Good afternoon. I'm going to do another example problem for y'all. Last time I did one that was inelastic, so they stuck together. This time I'm going to do a problem where it's elastic, where they are not together, they're apart, they bounce off of each other. So our scenario is as I have a 4 kilogram bowling ball, which is actually kind of a weenie bowling ball, is moving at 0.75 meters per second. It knocks against one sad, lonely bowling pin with a mass of 0.3 kilograms. Both the bowling ball and the pin move forward after the collision. If the ball moves with a velocity of 0.1 meters per second, how fast is the pin moving? Okay, so just a little scenario here. So here's our little bowling ball, little finger holes. And then, looks like it's smiling. I think I need to be around people. Oh, God. Okay, and here's our pin. It's a little sad. And then this one's moving towards it. This one is not moving at all. And then, kabam, they crash. And then and then the bowling ball continues to move forward, but now the funny looking pin moves forward too. We would expect it to move faster because it has less mass. Okay, let's put this in an if chart so that maybe we can think away through the math. Let's do the bowling ball in green. Okay, and the bowling ball is 4 kilograms, so I'm going to say that's 1 kilogram, 2 kilograms, 3 kilograms, 4 kilograms. And it's moving 0.75 meters per second. So let's say that this is 1 meters per second and this is 2. So that means it's going to be moving this much momentum. Okay, and then the bowling pin, we'll put it in red. It is at rest. Oh, Christmas colors. And then afterward, we have the same mass, but now it's moving a lot slower. So now it's down here with 0.1 meters per second, but it's still moving forward. And now I just got to figure out how much that 0.3 kilograms. So he's skinnier than the space that we have here. It's got to be skinnier than that. And we know it's going to move forward, but we don't know how much. So let's just put a bar here now for now, and then we'll see if we need to adjust the scale later. Great. So let's set up a momentum equation. So we know that our momentum initial is going to be equal to our momentum final, and we know our momentum initial is from both of these, and our momentum final is from both of these. So that means we have the mass of the ball times the velocity of the ball initially, plus the momentum of our bowling pin, which is the mass of our pin, times the velocity of the pin initially. And that's going to equal to the mass of the ball, the velocity of the ball final, the momentum of the ball in the final scenario, plus the mass of the ball, pin. I knew I was going to do that. Mass of the pin times velocity of the pin final. Okay, and what we're looking for is this guy right here, the velocity final for the pin. So let's plug in zeros first. I know that the momentum initial for our bowling pin is 0, so let's cancel that out. And then we want to get VPF by itself. It's added to this other phrase. There's a word for that. This other piece of the equation. So we want to subtract that away first to get it by itself. So we'll say MB VBI minus MB VBF equals MP VP final. Okay. So now the velocity we're looking for is multiplied by mass. So we're going to get rid of that by dividing that mass away. We'll do the same on both sides. Okay. So if I was going to rewrite this, I'm going to make this fancy. Since I noticed that both of these phrases are multiplied by mass of the bowling ball, I'm going to factor that out. And I'm going to make this the mass of the ball times the velocity initial of the ball minus the the ball's final velocity, and then divide that by the mass of the pin. Let's plug in some values. Squeeze them down here. The mass of the bowling ball we know is 4 kilograms. We know that the initial velocity, is going to be 0.75. And then we want to subtract away the final, which we know is 0.1. And we're going to divide that by the mass of the bowling pin, which is 0.3. So I'm going to get out my handy dandy calculator. And then do 4 times 0.75 minus 0.1. And then we'll divide that all by 0.3. And we're going to get 8.666 repeating. We'll say 8.67 approximate meters per second. So our scale in our initial scenario is totally off. So let's redo it. So let's make this look a little better. Get rid of this, get rid of this. We'll keep the same width. But now we got to get all the way up to like 9. Okay, so say 8, 7, 6, 5, 4, 3, 2. I couldn't quite fit it. Yeah, there's that. That's 9. And now they all fit. So that means we're way down here. Barely fits on the page. It's barely showing up with that 0.1 meters per second. And this is much taller. So imagine the same scale over here. This would be squished all to fit in this space right here. So that pin's going to move a lot faster. These are not realistic numbers. Okay, but hopefully the example helps you out and see the scenario. Again, we did not end up using that force time diagram because we didn't need to have any information on impulse. We could have figured out the impulse of both of those objects because we have their velocity finals and their initial velocities and their masses, but we just didn't need them for the problem. So hopefully this helps you guys out. Let me know if you have any questions.